Hi, everyone. My name is Will Jordan. I'm a software engineer at code.org, and welcome to my RailsConf 2021 talk, What the Fork? So, code.org is a nonprofit dedicated to expanding access to computer science in schools and increasing participation by young women and students from other underrepresented groups. Our engineering team develops a computer science learning platform for kids, which is based on a Rails application I've been a part of building and operating since 2014. And over the years, this Rails app has evolved and matured to support growing numbers of teachers and students. We now have over 1 million teachers and over 40 million students on our platform, and have translated our curriculum to over 60 languages. So this is a pretty large Rails application we're running. Our annual Hour of Code event in December introduces millions of students around the world to computer science, with local events in over 180 countries. This week-long event has served over 1 billion total sessions since it first began in 2013. And at peak traffic, our site typically serves over 10,000 requests per second during this event. So while operating and especially debugging performance, scalability, and reliability issues in our app as our infrastructure lead, there was one particularly magical method that seemed especially important and has always caught my interest, and that's the Unix fork system call. It's a tool that gets used all the time and that we mostly take for granted. You could call it the staple utensil of Unix-based operating systems. Here's fork being used, for example, in the Puma, Parallel, and Spring gems. At first, I only vaguely knew that fork creates a new process, and it took me quite a while to grasp its nuances and dangers, to appreciate its significance in Unix, and to understand how it maximizes Ruby performance on multiprocessor systems in particular. So in this talk, I'll share with you everything I've learned about fork. I've broken this talk down into 3 sections. 1, Unix fundamentals, where I'll look at fork and related system calls. 2, Ruby and Rails deep dive, where I'll look at the use of fork in Ruby in general and how it's used in the Spring and Puma gems in particular. And 3, tips, tricks, and experiments, where I'll review some best practices and share a couple of interesting experiments I've worked on. All right, first off, Unix fundamentals. What exactly is the fork system call? What does it do, and where did it come from? As a starting point, let's look at the current documentation from the Linux man pages project. Here it says, fork creates a new process by duplicating the calling process. The new process is referred to as the child process. The calling process is referred to as the parent process. So a call to fork duplicates a single process into parent and child so that each can run independently. And if the system has more than one CPU, they can even run in parallel. This parent-child distinction is important because the parent process can keep track of its children through their process IDs, and this creates a process tree covering everything running on the system. And the description here continues. The child process and parent process run in separate memory spaces. At the time of fork, both memory spaces have the same content, and memory writes performed by one of the processes do not affect the other. This is saying in so many words that the memory space in the child process acts like a copy of the parent's. It doesn't have to actually copy all the memory. Just needs to behave like a separate copy when writes occur. In modern systems, fork actually takes advantage of an optimization that's called copy on write, and I'll go into more detail on that later. The full documentation is much longer, but I pulled out one more note here worth mentioning. The child inherits copies of the parent's set of open file descriptors. Each file descriptor in the child refers to the same open file description as the corresponding file descriptor in the parent. This is a little abstract, but really important to how fork operates. In Unix, a file descriptor is used to represent not only open files on the file system, but also things like network sockets and pipes, which are input-output streams used to communicate between processes. This is really powerful, but also dangerous, and using fork effectively in more complex use cases usually requires carefully controlling these inherited file descriptors. I'll get more into that later, but first I'd like to cover the most common and basic use of fork, which is just to spawn a brand new process that executes another program. So for this, you follow fork with the exec function. Here's the man page for exec. The exec family of functions replaces the current process image with a new process image. There shall be no return from a successful exec because the calling process image is overlaid by the new process image. So fork exec is how you spawn a subprocess with a new program in Unix. And then if you want the parent process to wait for the child to finish before continuing, if you don't want them to run concurrently, then you can call wait. And here's wait. The wait system call suspends execution of the calling thread until one of its children terminates. Now I want to take a little digression here to point out one weird quirk of the Unix process model you might have heard of or come across, and that's the zombie. Here they say, a child that terminates but has not been waited for becomes a zombie. The kernel maintains a minimal set of information about the zombie process in order to allow the parent to later perform a wait to obtain information about the child. As long as the zombie is not removed from the system via a wait, it will consume a slot in the kernel process table, and if this table fills, it will not be possible to create further processes. If a parent process terminates, then its zombie children, if any, are adopted by init. As one example of this, a couple of years ago, Puma had a regression in how it waited on terminated worker processes that are listed in the PS utility here as defunct. This bug caused a zombie invasion in Rails servers everywhere. All right, back to Fork. Here's a simple example of the C interface of Fork. Checking the return value of the fork call lets you run different code paths in the child and parent. And the child branch calls exit here to terminate its own process. And it actually calls _exit, which avoids invoking any existing exit handlers you might not want to run when the child process exits. And then the parent branch calls waitpid, which is a variant of wait, to wait for the child process to finish before continuing. And you could also replace the child's printf call here with a call to exec if you wanted it to run another program in the subprocess, for example. So that's the basic C API. Now let's go into a bit of Unix history to understand the fundamental significance of fork in Unix-based systems. So the computer science term fork was coined just a few years before Unix in a 1963 paper by Melvin Conway as a model for structuring multiple processes and programs. And this paper influenced the designers of a 1964 computer research project at UC Berkeley called Genie. And that in turn served as an inspiration for the original Unix that was developed around 1969. I'd like to point out how essentially fundamental the fork call was and still is to the Unix operating system, as well as how much of a hack it was and still is. Dennis Ritchie, who co-designed Unix along with Ken Thompson, both pictured here, wrote, "The PDP-7's fork call required precisely 27 lines of assembly code." And this is the original assembly code on the right. I can't say I went through the trouble of deciphering it, but Ritchie described it as follows. There was a process table, and the processes were swapped between main memory and the disk. The initial implementation of fork required only 1, expansion of the process table, 2, addition of a fork call that copied the current process to the disk swap area using the already existing swap.io primitives, and made some adjustments to the process table. So that's it, just those 27 lines of code. He went on to write, "It's easy to see how some of the slightly unusual features of the design are present precisely because they represented small, easily coded changes to what existed. A good example is the separation of the fork and exec functions. It exists in Unix mainly because of the ease with which fork could be implemented without changing much else. So like I said, it was a total hack." So fork was one of the fundamental primitive operations in Unix from its very first version. And here's an early Unix man page for fork from 1971, where it says fork is the only way new processes are created. So the original fork worked well enough, but its implementation was relatively slow because it had to copy the entire process into a separate address space. This was not only slow for forking large processes, but it was also mostly redundant, especially when followed by exec for the common use case of launching a new program in a subprocess, since exec immediately replaced the address space with a new program. So to address this common use case, in 1979, BSD3 added vfork system call as an optimization specific to fork exec. Instead of copying the address space, it shared the existing one with the parent process, since it's going to be replaced by exec anyway. And then to avoid memory contention, it suspends the parent process until the child calls exec. This was efficient for a simple fork exec, but it's pretty dangerous for any code that might happen to write to memory in between. And vfork had lots of other race conditions issues to deal with, like bad interactions with signal handlers or other threads on the parent process and so on. So in 2001, the POSIX standard introduced POSIX spawn to Unix, which wraps up the fork and exec pattern into a single system call. So it can be as efficient as vfork and is sometimes actually implemented with vfork under the hood while avoiding all of the different safety and race condition issues. So if you can use it, this is the recommended API for launching new processes today. The next important optimization of fork was copy on write, which various Unix systems implemented in the 80s, for example, AT&T's System V Release 2, which is a really popular Unix system. It leverages features of the MMU, or memory management unit, of a CPU architecture, for example, x86-64. So it needs that hardware support in order to function. An MMU typically uses a page table to map pages in the process's virtual address space to physical memory and then handles the translation back and forth. After a fork, the page table is copied to the child process, and then the OS kernel marks all the pages as read-only so that any future writes to the page from either parent or child triggers a page fault. And then when a write occurs and the page fault gets trapped by the operating system, it can copy the page to a new location in memory, and then the page table is updated. So this makes fork both faster and more memory efficient, since it doesn't actually need to copy any memory pages until they're actually modified. This optimization makes normal fork nearly as fast as vfork, but since fork still copies page tables, vfork is still slightly faster for very large processes. Finally, beyond fork, there's threads. And Unix originally used only processes to run programs in parallel on multiple CPUs and also just to provide general concurrency. However, since processes were traditionally relatively heavyweight, they took a long time to spin up. Other systems implemented threads, which are sequential flows of control like processes, but that shared a single address space instead of copying them. Kernel-level threads were added to various Unix systems in the 90s, and a POSIX thread standard called pthreads was published in 1995. This standard defines that a process contains one or more threads, and for every process there is an implicit main thread. And so when a process calls the exit function to terminate, all of the other threads are terminated as well. The standard also says that on fork, only the calling thread is running in the child process, so no other running threads are copied over. In general, there are three models for mapping user-level threads, or the threads that are presented to user programs through an API like pthreads, mapping those to kernel-scheduled threads that are running under the hood. The first model is many-to-one, or straight user-level threads. These all run on a single OS thread, and all of the context switching between threads is handled by the program itself. These can be really fast since there's no overhead of entering and exiting the kernel for a system call, but they can't run in parallel on multiple CPUs. The threads aren't visible to OS utilities or profilers, and a blocking system call can stop all threads if it's not handled properly. The next model is one-to-one, where the kernel-level threads or native threads are passed through more or less directly to the user-level API. This is the model you find in most pthread implementations today because it performs really well and it's relatively simple to implement. And finally, there's many-to-many or hybrid threads. You can theoretically get the best of both worlds, where your program can spin up M threads, and then the mapping magically figures out the best way to multiplex them onto N threads in the kernel that can run most efficiently. This was a more popular model for pthread implementations in older Unix systems, when I guess there was a lot more overhead to creating new kernel threads. But today, the one-to-one model is pretty much won out in performance and simplicity. That said, the M-to-N model can still be the holy grail of performance, not for pthreads directly, but as a construct within a programming language framework. Go's Go routines, for example, are a pretty mature concurrency model with a scheduler that efficiently maps large numbers of user-level Go routines onto the minimum number of OS threads necessary to utilize all CPU cores on the system. In modern Linux, threads and processes are actually two types of tasks. There's a more abstract, generic clone call that underlies all task creation, and both processes and threads differ only in their degree of resource sharing. So while traditionally threads are considered lightweight versus processes, in modern Linux, their performance is actually very similar since they share a good chunk of implementation under the hood. And they both share the same exact scheduler. They're scheduled exactly the same. All right, so that's everything on fork in Unix. Next up is the Ruby on Rails deep dive. Here's a basic concurrent programming example that creates an array of 10 Ruby threads that each do some heavy work and then waits for all the threads to finish at the end. Now, ideally, this code would run in parallel on a powerful machine with multiple CPUs, and on some Ruby implementations it does. Unfortunately, it doesn't in CRuby thanks to the GVL, or global VM lock. The one exception to this is when the GVL is explicitly released by a function in Ruby's C API, which can happen for all I/O operations, many system calls, and some C extensions. However, because separate processes will have their own separate GVLs, fork can actually allow similar Ruby code to run in parallel, even on CRuby. Here's Ruby's API for fork. There's two ways to call it, with or without a block. If a block is specified, it's run in the subprocess or child process. Calling without a block is similar to the C API where the call returns twice, with the child's process ID returned to the parent and the nil returned to the child. Though I find the block version a little clearer and easier to use, so that's what I tend to use in practice. Here's a parallel processing example using fork. The fork block is executed 10 times, creating 10 child processes. Each child process does work and then prints a line to standard out with the unique process ID, that's the $2 signs there, and the parent process waits for all of the children to finish. Now note that the order in which each child process finishes and writes to standard out is not fixed, so the final printed output is not in order either. Also note that all of the children put statements all print output to the same terminal, which seems straightforward, but how exactly are these streams getting combined? The answer is standard output is a standard IO stream represented by a fixed file descriptor, number 1 by convention. And one of the properties of fork is that child processes inherit copies of the parent's file descriptors. So the output is all written to the same stream that's connected to the terminal, which is the standard out of the parent process. Now this next example shows how the streams and file descriptors work a bit more explicitly. Here an anonymous pipe is created at the start before any forks to pass the output messages from children to parent, and noting that the child inherits copies of the parent's open file descriptors. The parent then reads the messages from the R end of the pipe and then prints them to standard out. So you get the same output and it's still not in order. So here's a further modified example that prints the output in order. It does that by creating a separate RW pipe for each child and then reads and prints the output from each pipe in the original order in the parent process. Finally, the existing gem parallel already wraps up this pipe fork pattern into a simple API. All right, so for this next section, we'll look at some more complex use cases. First up is Spring, the Rails application preloader. The way Spring works is that the first time Spring is run, it creates a background server process that initializes your Rails application for a particular environment and then waits for a signal from another process to quickly serve up a new preloaded Rails process, for example, to run a console or test command. Here's a process tree diagram of a Spring server process running, hosting a single Spring app process where the Rails app was fully initialized and 2 Rails console child processes below it. Separately, there you see 2 bin/Rails console commands are running, which are the original command processes, the ones that the user invoked via the command line interface. And so these must be somehow indirectly connected to the 2 Rails console processes there. Let's see what exactly is happening and how fork fits into this picture. So here we see the code that invokes fork in the application class. It receives the 3 standard streams on a client socket through the receiveIO method, and then replaces its own standard streams with the received ones through the reopen method. And then it reads some JSON containing command arguments and environment values. Then it calls fork, does a lot of stuff, and eventually at the end of the fork block, it calls the provided command still within the child process. So when a new client connects to this Spring app process through a Unix socket, it passes along its standard in, out, and error file descriptors to the Spring app using a special feature of Unix sockets. The system call is send message, receive message, and it's wrapped up as send IO and receive IO in Ruby. And then these streams are then reopened in the Spring app process. And the reopen method in Ruby corresponds to the Unix dup2 system call, which just copies one file descriptor over another, replacing it. So this allows the new process to behave as though it magically became a fork of the existing preloaded application, even though it's still an entirely separate process. So this is a diagram showing how the different Spring processes relate to each other. At the bottom left, the Rails console commands are run in the processes, which pass their IO streams to the server up to the top left. The server manages a set of application manager objects, one corresponding to each environment. And then those spawn separate Spring app processes that load the Rails app from scratch. And then the manager passes the streams into these processes. Then the application class in those Spring app processes calls fork to create a copy of the preloaded app process and then passes the streams onto them, where the provided command is then executed. So that's how Spring works. Next up is Puma, a Ruby web server built for concurrency. Here's what Puma's cluster mode looks like, running with 8 workers. On the right is the process tree where all 8 cluster workers are forked from the parent process. And here's the code from the cluster mode of Puma that calls fork to create these separate worker processes. So to understand this better, here's a diagram of how the main server loop works in Puma and how its hybrid model of threads and processes works together. So when the parent process running in cluster mode first boots up, it loads the rack application, executes the listen system call, which creates a TCP server socket bound to an IP address and port number, and then calls fork to create a number of cluster worker processes, each of which run a server loop. And then this server loop calls select, which waits for incoming data on their socket, and then accept, which opens a TCP connection that then gets passed to one of several threads in a thread pool, one for each worker. And in the thread pool, the HTTP request is processed, the rack application is called, and then the response is written back to the TCP connection. So this model of multiple threads on top of forked processes allows Puma to be particularly effective for IO-bound loads compared to single-threaded servers because it can handle multiple requests on the same process. This benchmark here shows multi-threaded Puma handling almost twice as many responses per second as single-threaded Passenger and more than 3 times as many as single-threaded Unicorn. However, for a long time, there was a tricky performance issue when running multiple threads in Puma. This other benchmark at the top here shows multi-threaded Puma's performance actually falling behind Unicorn Passenger in a database query test. And these graphs below are from a performance regression I observed when I was first migrating Code.org's Rails app from Unicorn to Puma. You can see the 99th percentile latency had much higher spikes, and the Unicorn graph is a lot more stable overall. And similarly, a similar issue was reported by an engineer at GitLab, where this same performance regression was also preventing them from migrating their apps from Unicorn to Puma safely. This graph shows the percentage of time waiting on a database request was much higher in their Puma app server compared to their Unicorn one. So it turns out that this performance issue had to do with how connections on the socket shared through fork were being unevenly routed across processes, which ended up causing contention among multiple threads in a process. So to illustrate this, in this example diagram, all 4 workers have a thread that's actively waiting to accept new connections from the socket through those inherited file descriptors. In this example, cluster worker 1 is busy processing a single connection, but since it still has an extra thread ready for more work, it's still going to be accepting new connections as well. When the next connection arrives, there's a race among all the workers to get it. Basically, the first thread that makes it from getting woken up to calling accept wins the race. Let's say that's worker 3 in this example. So it starts processing the connection in its thread pool, and the 2 requests in the system are now getting handled in parallel. However, let's say the next connection gets accepted by worker 1. It adds the connection to the thread pool since it still had a worker thread available, but that work then encounters contention from thread mutexes or the GVL, so it runs a lot more slowly. In order to run Puma most efficiently, it should route new connections in a balanced way across all the processes, while still allowing busy workers to accept new connections as long as all the work is being evenly loaded. So one possible approach to this is to actually accept connections before the fork and use a feature of Unix domain sockets to pass file descriptors from the parent process to its children, kind of like how we saw in Spring. The actual Unix calls are a bit complicated, but Ruby wraps them up nicely in the send.io and receive.io methods that we saw. The trade-off here is that there's some overhead in having the workers report to the parent their current load, and there's also would be now a critical thread in the parent process responsible for all of the incoming connections. And so if that thread gets blocked or crashes for some reason, then the whole system gets blocked up and goes down. Another approach is to have the parent do nothing, and then each worker binds their own separate socket. This is possible for them to all bind to the same port if you use the SO reuse port option in the Linux kernel. Now this would be nice and distributed, but the implementation of SO reuse port distributes connections across the sockets based on a hashing function. And this function wouldn't know how to distribute based on the current load of worker threads in the process. So there'd still be a possibility of connections getting unevenly bunched up on the same process. So this is a clever and relatively simple approach that Camille from GitLab contributed, and it's actually what current versions of Puma use to finally fix this performance issue. All it does is have each server inject an extra tiny wait in between the select and accept calls when the worker is busy with another connection. So you could see, like, for example, worker 1 here has a single request being processed on its thread pool, so it adds a wait before it runs accept. This way, any idle workers are more likely to pick up the connection first. And then if they're all busy, then a lightly loaded server will still pick up the connection after a small delay. Okay, now for some tips, tricks, and experiments. As we saw, the earliest and most common use case of fork is to spawn a brand new process using the fork exec pattern. However, in modern Unix systems, you should really use spawn instead of doing a fork exec yourself to avoid dealing with the various race condition headaches on your own. You can either use the POSIX spawn system call function directly, or Ruby provides the process.spawn, which is a similar API, even though it still currently does fork exec under the hood. It can still handle all the tricky race conditions on its own for you. So besides launching a new process, the next general use case of fork is to run code in parallel across CPUs. This model is great when you want to run code that's fully isolated by default, since there's no need for mutexes or generally any thread-safe code. And it's particularly important for Ruby because it lets you bypass the GVL, which gives it a great advantage versus running threads concurrently. Finally, another use case for fork is to take advantage of how it efficiently copies the entire memory address space of a process using copy on write. This is what lets you do things like preload a large application in a fork server process, like we saw in Spring. This same technique is also heavily used in other real-world systems, such as a fuzzer like APL or the Android process launcher. It's called Zygote. Finally, similarly, fork can also be used to freeze a consistent snapshot of fast-changing data in memory to run a kind of background save process. This is actually how Redis provides data persistence by taking point-in-time snapshots at regular intervals with minimal impact on the main process that continues to serve requests. So here are a couple of tips on how to design a good fork server. The main piece of advice is to preload as much as possible into the fork server process before forking. So this would be in your initializers in Rails. This can be a bit of a balancing act since you want to make sure you don't preload anything too unique that isn't going to be used too often by all the forked processes, or any data that might change too frequently so that it would just become obsolete in a long-running process and just take up memory. Beyond that, specific to Ruby, you want to make sure to do what's called a Nakayoshi fork to optimize memory pages for copy on write in Ruby. More accurately, this is kind of a workaround for a copy on write regression that was introduced in the generational garbage collector in Ruby 2.2. Unfortunately, the attribute that marks an object's age is stored directly with the object instead of in a separate copy on write friendly bitmap. So running garbage collection after a fork if it updates an object's age, then the memory page gets written and is no longer shared across the processes. But by running GC 4 times in a row, which is more than the max age of 3, it marks all of the existing objects in memory old, and so then their age won't get updated anymore, and so they're copy on write friendly again. It's also worth mentioning that gc.compact before a fork might theoretically help with copy on write efficiency because it would reduce fragmentation of Ruby's heap, and that could make existing objects less likely to need to be moved around later. However, I haven't really observed any significant effects or improvements in my own testing yet with GC Compact. Maybe some future work and profiling on this can make memory compaction more effective for copy on write efficiency, or maybe I just wasn't testing the right thing. Finally, transparent huge pages can destroy copy on write efficiency because then tiny changes in memory could cause much larger chunks of memory to be copied. Thankfully, Ruby disables this feature automatically, so you don't have to worry about it. For using fork for parallel processing, the big general tip is just to fork one process per CPU to maximize performance and memory usage. This way, each process has a full CPU to itself, and you can theoretically hit 100% utilization with a CPU-heavy workload. However, for I/O-heavy workloads, sometimes even more processes or even multiple threads per process, as we saw in the Puma server, could work even better. Beyond this, running many fibers on a process can even be more efficient than threads because it reduces the OS context switching overhead by handling all the scheduling at the user level. Finally, to maximize performance in Ruby 3 onward, you might want to start experimenting with ractors instead of forked processes when possible. As I understand it, ractors use kernel threads under the hood just like the Ruby thread object, but they manage each a separate VM lock. So you can run multiple ractors in the same process and they can run Ruby code in parallel, unlike threads. The trade-off is that any objects the ractor touches need to be marked as immutable or specifically owned by that ractor. That's its concurrency model. So it's not going to be easy to run your whole Rails app across multiple ractors instead of multiple processes anytime soon. That said, for small chunks of isolated code, this could still be a good alternative to using processes for parallel processing. The main advantage of reactors over forking processes is not actually performance, it's just that it can improve memory efficiency, since copy on write memory isn't 100% efficient in sharing memory because of fragmentation and movement of objects around both in the Ruby heap and in the low-level memory allocator. Message passing between reactors could theoretically perform better than IPC-like pipes communicating between processes. However, I haven't seen any benchmarks confirming this advantage yet, so that's still up in the air. Looking toward the future, if and when reactors get more mature, using many fibers per reactor and then one reactor per CPU could possibly reach that M by N threads holy grail performance I talked about earlier. So here's my final set of tips to help make your code fork safe. First, remember that @exit handlers are copied to the child and run in both processes. So you need to either add logic in the handler to ensure the process ID still equals the parent before executing, or you have to call exit bang when terminating the child to skip any handler registered by the parent. Next, be careful about sharing open file descriptors across processes. Make sure to protect any open network connections by closing them in the child process so that they don't get accidentally used by both processes at the same time. Finally, remember that background threads aren't copied to the child after a fork. You have to remember to restart important threads in the child after the fork, or just design the system with the expectation that they'll only be running in the parent process, and then remember to clean up any associated state afterwards. All right, for the last part of this talk, I have a couple of fork-related experiments I'd like to share. The first one is a Puma fork eval server. This is a simple, minimal fork server interface I've written as a Puma plugin. The idea of this plugin is to quickly and efficiently run code in your preloaded rack app. The general use cases are to spin up an interactive console like Rails console to run one-off or scheduled rake tasks that might need access to the rack application, or even to spin up asynchronous job processors running on a separate process, but that might still want to reference parts of the Rails app in their application logic. I like to think of this experiment as a kind of Spring for production. It doesn't create any extra application copy in memory like a separate Spring server does. Instead, it forks to run commands from the existing preloaded Puma process. There's also no risk of extra stale app versions or having to keep the Spring process in sync with Puma. Instead, it just runs the exact code already being served to your users by Puma. And so you can manage updates the same way you manage your production deployment lifecycle. And this is the bulk of the plugin code. It's not very much code. On the left is the server code that runs in a background thread on the Puma parent process. And on the right is the client code that gets invoked by a command line script. The server just listens on a Unix domain socket, and it runs fork for each new socket connection it receives. Within this fork, the child process replaces its standard in, standard out, and standard error streams using reopen with 3 file descriptors that it receives through the receive.io command. Then it just reads a string from the socket until the client closes the connection and then calls eval on the string it received. The client code is even simpler. All it does is it opens up a connection on the server's domain socket, sends its 3 standard streams using send.io, and then writes the code it wants to eval to the socket. That's it. This is basically just a super stripped down version of the core logic that Spring does to run its own fork server that can run commands in a preloaded app. It's not completely bulletproof yet. It doesn't do things like forward signals to the forked process like Spring does, and it hasn't been tested on all the kind of things all the kinds of commands Spring is compatible with, but I thought it would be an interesting start to share. The next experiment is also based on Puma. This one's not a plugin, but a new feature that I merged as a PR last year and was released as part of Puma 5. The general idea is that in some cases, it's possible to optimize copy on write efficiency on long-running servers further by making the assumption that as a server serves requests for live traffic, the app grows and accumulates additional objects in memory that could be shared across all of the running worker processes. So by what I call reforking workers from a single running process, it's possible to reshare the bigger application and then re-optimize the copy on write memory pages shared across them. So to make refork possible, I had to change the process hierarchy around a bit, and that's shown here. Instead of forking all of the workers directly from the parent, when the fork worker option is enabled in Puma, only worker 0 forks directly from the parent, and all other workers fork off of that worker after the app is loaded in the server. Then to do a refork, which can either happen automatically after a certain number of requests or through a control signal sent to the parent process, all of the workers greater than 0 get shut down and then just get recreated from worker 0 again by fork. Here's what the process tree looks like with fork worker enabled. So to test out the performance of Refork, I wrote this very simple contrived example rack app. In the rack handler, all this app does is it lazy loads a really big object as a global variable. And in the real world, ideally, we could just refactor this app to preload this object outside the handler so it gets loaded before the initial fork. But this is a contrived example, and sometimes this kind of refactoring is not as easy as this for big and complex apps. So for this benchmark, I launched the Puma server, ran work, which is a load testing tool, for about 20 seconds. And then I ran a function PSS that would check the memory usage. And then I ran the refork command to trigger a refork, ran work again, and then ran PSS again to check the final memory usage to see the difference. So PSS, or the proportional set size, is the best measurement of memory usage in a process that shares copy on write memory. PSS is defined as the process's unshared memory, or USS, plus a proportion of each shared memory chunk split across all the processes sharing it. So you must use PSS to accurately measure copy on write optimized processes. If you measure RSS, or the resident set size, instead directly, then the shared memory would be counted multiple times for every place it's being shared. To measure PSS, you can use either the smem utility or just read a special path on the file system directly. So for this test, I used this Ruby script to read the process IDs of the Puma workers, and then read their PSS values, and then just added them all together. So here's the final result of the test. Before the refork, our memory usage was almost 5 gigabytes, and then after the refork, it gets reduced down to around 1 gigabyte. Here's another view of that using smem to go into more detail. This is the cluster after the first run of work. You can see each worker's PSS is about 726 megabytes, and most of that is unshared, or USS. And here's the view immediately after running Refork. You see the RSS is still just as high, but the PSS is much lower, under 100 megabytes per process, and the unshared amount, or the USS, is tiny. It's only around 5 megabytes per process. Here's the view after the next run of work. There's about 100 megabytes of unshared memory per process, and so the total PSS is now a little under 200 megabytes. This is still much lower than the original PSS of 750 megabytes per process. And here you see the RSS is still as high as 750 as well. So there you go. Using Refork and Puma can reduce your memory usage up to 80%. Obviously a very exaggerated result. So I wanted also to show what this might look like for a real production Rails app. This is a comparison test that I ran on 2 production front-end servers running Code.org's Rails application, both serving live traffic, both AWS EC2 instances with 40 CPU cores. This graph is showing total memory usage as a percentage on the left y-axis. The orange line is the baseline instance, and the blue line is one where I ran the refork command a couple of times. You can see the 2 spikes in the graph are where I triggered the command. And then the green line there is just a calculation of the difference between the two as a reduction percentage. And that's the y-axis on the right. You can see immediately after the refork, the memory usage drops significantly down from 40 to around 20%. Then it creeps back up again as memory gets modified and the processes start to share less total memory. However, the reforked server still used significantly less memory than the original server, around 20 to 30% less in this app. And so this is a real production app. So whether this technique is helpful or not probably depends entirely on your app's unique workload and how important memory efficiency is to your production environment. In any case, I hope this experiment was interesting to some of you. All right, that's everything I have to share about Fork. Thank you so much for listening. I hope you learned something from my talk. And thank you to the RailsConf organizers for giving me the opportunity to speak and present on this topic, and to all the Rails developers, organizers, and maintainers in general for just fostering such a great community and delivering a bunch of excellent open source software. I look forward to more conversations in our RailsConf Q&A sessions and beyond. Thank you very much.